Hello everybody and welcome to the next presentation in the NAME training course. My name's Helen Webster and I'm one of the scientists in the Atmospheric Dispersion and Air Quality group at the Met Office, and I've worked on NAME for a number of years, particularly on the development of the model. This presentation is going to tell you a bit more about NAME, in particular what a Lagrangian model is and some of the physical processes that are represented within the model. So what are we trying to do? We're trying to estimate the dispersion of airborne matter. And for this we need three main components. First of all, we need to know about the emissions. We often refer to this as the source term. So what is being emitted? How much is being emitted, where is it being emitted from and when, and other properties of the emissions such as whether it's a gas or a particle, whether it's buoyant, whether it's hot or not, and such other things. We then need a model to represent the dispersion of the substance, and here we're going to talk about NAME, which is the Met Office's Lagrangian atmospheric dispersion model. And then we need to drive our model with a description of the meteorological situation. And generally we use 4D NWP Met fields for this. These generally we take from the Met Office's own unified model, but we can also use other metadata sources. And for short ranges, we can actually use observations from a single site. So as I mentioned, NAME is a Lagrangian model, and I'm going to tell you more about what this means throughout this presentation. And it also represents a number of physical processes, and we'll go through a number of these, well, some of the key ones, such as turbulence in the atmosphere, how this disperses material, deep convection, deep moist convection throughout the troposphere, deposition, that's the removal of substances from the atmosphere to the ground, and sedimentation, so that's the falling of heavy particles by gravitational settling. And then there's also a chemistry scheme within NAME as well, but we'll go through each of these in turn. So to start off, as I mentioned, NAME is a Lagrangian particle dispersion model. So let's talk a bit more about these models. So in a Lagrangian model, we follow air parcels. So given a particular air parcel, which at a particular time is at a specific location, we can interrogate our input metadata to determine the wind speed, temperature and other meteorological variables at that air parcel. And we can move our air parcel within our model according to these meteorological variables over the model time step. At the new point in space and time, we can repeat this procedure and we can track the movement of this air parcel through the atmosphere. Each air parcel also carries a specific amount of the material that's being modelled, and we can also track how this mass of the material changes over time. This is different to a Eulerian model where the meteorological variables and the concentration of the material being modelled is represented and held on a fixed grid. So back to Lagrangian models. These air parcels are usually referred to as model particles. That's not to say that they're real particles, because these model particles represent a certain amount of the emissions, which can be either a gas or a particle. As I've mentioned already, the model is driven by input meteorological fields. It's an offline model, and the input fields generally come from numerical weather prediction models, but at short range we can use single site observations. And the model has a number of subgrid processes within it that are parameterized. Let's start by considering purely advection due to the mean ambient wind. Imagine we have a particle located here at 0900 hours. We can interrogate the input NWP data to determine the mean ambient wind at this point in space and time. This is shown here using this green arrow, the length of which signifies the wind speed and the direction, the wind direction. And we can move our particle using this mean ambient wind over the model time step. And it can be found at a new location shown here. We can repeat this process at this new point in space and time. We interrogate the NWP data, finding the mean ambient wind and affecting our particle over the new model time step at this time. And we repeat again and again and again. So at the end of our time period, we have our particle at its final location, having been advected through a number of positions and model time steps. And at each point, the particle has moved to the next point based on the local mean ambient wind. This gives us the mean trajectory of the particle due to the mean ambient wind. If we were to release many particles at the same location and time, they would all follow the same mean trajectory. However, we also need to take into account the effects of small scale motions not resolved by the input NWP data. For example, small scale three-dimensional turbulent motions. And we do this by adding on random turbulent components to the particle advection using random walk techniques. So let's go back to our schematic again and imagine that we're releasing two particles from the same position. We obtain the mean ambient wind at this position in space and time from our NWP model and advect our particles according to this mean wind. But we also add on a random turbulent component due to the effects of these small scale motions. So what we find is that these two particles end up at slightly different positions. We then repeat the process and find the mean ambient wind at these new positions and advect our particles according to this, adding on another random turbulent component. And we repeat again over a number of model time steps. And what we find is that these two particles that started off together have now dispersed and have separated. This is the equation used for advection within NAME. It's quite simple. The new position of the particle is given by the position at the previous time step plus an advection due to the mean wind and some random turbulent components over the model time step. So it's advected by a wind which has components due to the mean ambient component and the unresolved components. So here again is our trajectory simulations. So again, releasing lots of particles from the same location at the same point in time. And you will find that over time they spread out, they disperse to produce this ensemble of trajectories, and it is the ensemble of trajectories that represents the spread of the material. So let's put the trajectory plots side by side to compare. On the left here we have advection purely by the mean wind, ignoring any subgrid scale motions such as turbulence. We release many particles, but they all follow the same mean trajectory. And this is the same in X, Y and Z. Here we've got height up the side and time, and you can see that they're all following the same trajectory. When we add in the effects of small subgrid scale motions such as turbulence, we find that when we release many particles, they all follow slightly different trajectories, and the spread or the dispersion is represented by the ensemble of these trajectories. And this applies both in X and Y and in Z, so they spread both in the vertical and in the horizontal. I mentioned that NAME uses random walk techniques to represent small grid scale motions. It actually has two schemes. Firstly, a simple diffusion scheme, commonly known as the long range scheme, which is cheap and efficient to use and is based on homogeneous turbulence profiles. There is also a short range scheme which uses velocity memory. That is to say that its velocity at the next time step depends on the velocity at the previous time step. It can be quite expensive to use this scheme, but it does give a more complete description of the dispersion near to source. For the reasons of expense, though, it is commonly not used, but if it is, it tends to be used only for a short while before switching to the cheaper long-range scheme. We're now going to move on to discuss some of the physical processes represented in NAME and how these are parameterized. The transport and dispersion of material in the atmosphere depends on a number of physical processes and on the meteorological situation. This is a schematic of the procedure. Here we're trying to predict the transport and dispersion of a plume from a power station stack, where it goes, its dimensions, and being able to predict the concentration at particular points. We start with the emission detail. How much is being emitted, from where, at what height, and other properties such as the temperature of the release and therefore whether it's buoyant. The downwind dispersion is governed primarily by the mean ambient wind, and this will vary depending on the height of the plume. The spread of the plume is dependent on the turbulence, and this takes on two different forms. Firstly, mechanical turbulence caused by the wind blowing over a rough surface. And secondly, convective turbulence, which determines the height of the boundary layer and will depend on the time of year, the amount of sunshine and cloud cover. NAME also includes the representation of loss processes, and a key loss process is deposition. Deposition is the removal of material from the atmosphere by transport to and subsequent uptake by the ground. It comes in two forms, wet deposition and dry deposition. Wet deposition is the removal within precipitation. Dry deposition is the removal in the absence of precipitation. and the uptake at the ground is strongly dependent both on the species and the meteorological situation and the land surface type. Sedimentation is the gravitational settling of heavy particles, and that forms a contribution to dry deposition. It's modelled within name using the concept of a sedimentation velocity, which depends on both the size, shape and density of the particle. Dry deposition is modelled using a simple loss equation where the constant of proportionality is known as the deposition velocity. The deposition velocity can be calculated within name in a variety of ways. The simplest case is where a fixed value dependent on the pollutant is specified, but it can also be calculated using a resistance analogy where the deposition velocity is given by the inverse of the sum of three resistances. Firstly, the aerodynamic resistance, which represents the efficiency with which material is transported to the ground by turbulent motions in the atmosphere, and that bit is independent of the pollutant type but dependent on the meteorological situation. Secondly, the laminar sublayer resistance, and this represents the resistance to transport by molecular diffusion across the thin quasi-laminar layer adjacent to the surface, and it's formulated differently for gases and particles and depends both on the meteorological situation and the species. And lastly, the surface resistance, which characterises the resistance to capture by the surface, and that's dependent on both the pollutant and the underlying surface. For wet deposition, we also use a simple loss equation. Here the constant of proportionality is known as the scavenging coefficient. There are two parts to wet deposition: below cloud scavenging or washout, in which material is swept out by falling precipitation elements, or in cloud scavenging or rainout, where material is absorbed directly into cloud droplets or ice nuclei as they form. The scavenging coefficient is dependent both on the precipitation rate, the cloud type or the precipitation type, e.g. snow or rain, the process, be that washout or rainout, and for particles, the size of the particles. Atmospheric convection plays an important role in the vertical transport and mixing of airborne pollutants. Mixing within the convective boundary layer is represented as part of the turbulence parameterization. However, there also exists a scheme in name to parameterize deep moist convection within the troposphere. Convection is subgrid when name is run with global met data, and hence it needs to be parameterized. The scheme in name uses a mass flux approach, which includes both entrainment and detrainment into the convective cloud. The number of particles that are entrained at each level is given by a stochastic approach. Mass fluxes for the scheme are not yet available from the UN, and so these are parameterized using convective precipitation. And the entrainment and detrainment fluxes are calculated in a similar way to the scheme in the UN. The scheme is a simple 1D model. It has 59 vertical levels, and for each level, the number of particles that move is calculated in a probabilistic way. Particles are entrained into the convective cloud. They move vertically upwards and are detrained back into the environment. This updraft is compensated by a subsidence flux. And at all times, particles must fulfill the well-mixed condition. NAME has an explicit sulfur and nitrate chemistry scheme. It has both gas and aqueous phase reactions, with over 100 reactions modelled for both biogenic and anthropogenic species. Other chemistry schemes exist in NAME, including a simplified sulfur chemistry scheme and an iodine chemistry scheme. The chemistry schemes are generally applicable to air quality and volcanic chemistry type runs. An Eulerian model has been developed within NAME to represent the evolution of a scalar field. It can be used in conjunction with the Lagrangian model. That's to say that mass can be released on particles and transferred to fields after a specified time. It's fully flexible, and that time can vary from one source to another. The model uses a semi-Lagrangian scheme, which is consistent with the unified model. The semi-Lagrangian scheme allows the use of large time steps, making it efficient. And the user needs to specify a computational grid for the Eulerian model. Vertical diffusion in the Eulerian model is represented using a Crank-Nicolson method. And the Eulerian model shares much of the functionality of the Lagrangian model, for example, representing wet and dry deposition and sedimentation. There are a number of other parameterizations within NAME, and here we mention just a few of them briefly. For decay processes, there's a simple basic half-life decay scheme for single radionuclides. There's also a more advanced scheme modelling decay chains through a series of radionuclides. And there's also a virus decay scheme, which is useful for biological species. NAME can also represent plume buoyancy. There's a momentum and buoyancy driven plume rise scheme used for isolated sources such as power station stacks. And there's also a specific volcanic plume scheme, which takes into account the effect of the ambient wind on the rise of the volcanic plume. NAME also has an urban scheme representing the increased dispersion within urban areas. And there's much more. At this point, I'll recommend that you have a look at the NAME user guide for more details. We're going to finish this presentation by looking a bit more about outputs from Lagrangian models. We've already talked about trajectories within the model and following NAME model particles throughout the model atmosphere. But how do we convert this into the product that we want? Say, for example, forecasting air concentrations. We do this by putting an output grid over the region of interest. This is specified by the user. We calculate concentrations within each grid box by summing the mass of the particles within that grid box and dividing by the volume. The resolution of the concentration field is very much determined by the output grid box resolution, as you can see. If we choose a smaller output grid box, we will get much finer detail. However, we need to be careful that there are enough model particles for the size of our output grid box. Lagrangian models calculate concentrations by summing the mass on particles within a grid box. If we take smaller output grid boxes, then we may suffer from an issue known as noise, in which there are very few particles within each model grid box. We may need to increase the number of particles if this is the case. Here is an illustration of noise in a Lagrangian particle model. On the plot on the left-hand side, we have released 300,000 particles, and the resulting concentration fields are smooth. Whilst on the right-hand side, we've released just 7,500 particles, and the concentration field is quite noisy. This tells us that we haven't released enough particles. To overcome issues with noise, you have a number of options. Firstly, you could choose to increase the number of particles released, but this will have implications on your model runtime. Alternatively, you could choose to increase the amount of averaging of the output. For example, choosing a larger output grid box will increase the spatial averaging, or alternatively, you could increase the vertical averaging or the temporal averaging. In all cases though, I recommend that you plot your results to check for noise. And if in doubt, try increasing your number of particles released to check that results do not change much. So that is the end of this presentation. For more information, consult the NAME user guide, which also contains a number of references for further information on the parameterizations mentioned in this talk. Thank you for listening.